Hi, Year 12s. So today's subtopic that I'll be going through is 3.6, which is amines. Now, you'll be able to identify amines by the NH2 group, or at least primary amines, which I'll cover in a second. The name of these molecules will have the ending or the suffix amine. That can be modified depending on how many amine groups there are in the molecule, but either way, you're going to see amine if it is, in fact, an amine. Now, as I mentioned before, I mentioned the word primary. Now, primary amines are one of the three that we're going to be looking at. Now, a primary amine has a nitrogen atom that is bonded directly only to one carbon. It follows, hopefully it's obvious that it follows the second degree amine is then attached to two carbons. So we have a nitrogen in the middle here attached to one carbon group here and then another carbon group here. And then the last one, which is a tertiary tertiary amine, has our nitrogen here attached to three R groups. Now, we are only actually going to have to name, in this course, primary amines. So we only have to name the primary amines, which is nice, so it saves us a bit of effort. And before I move on to doing that, I want to just remind you that primary amines, they are terminal. So, like, in other words, they don't form part of the carbon chain. They are they're sort of an end to it, because they are attached to a carbon, but then they are attached to two hydrogens as well, which means we cannot continue with that. Now, secondary and tertiary can. You've got an R group here, and you've got other bits coming off there. But we don't have to worry about naming those, at least. Now, down to naming them. So they have quite a similar naming scheme to before. The difference is that actually, no big difference yet. But we'll start with methenamine. So that will be our carbon here with its three hydrogens and then an amine group coming off of it. Then we move up to ethenamine. So that will be two carbons and then with our NH2 attached. And what you'll notice is there are no numbers associated with those two first structures. And that is because the number is meant to be telling you where that nitrogen group is if it's ambiguous. Now, with methenamine, there's only one carbon. In ethenamine, there are two carbons, but if it's attached to this one here, as it is in this drawing, that is an identical structure to if it was attached to this one instead. So because either option are identical, you don't have any numbers. Now, we will get a number once we get up to a carbon chain, which is 3 carbons long, because you could have it attached to an end carbon, which gives us propan-1-amine, as you can see drawn here. You could also put that amine on the middle carbon, in which case it would be a propan-2-amine. Now, I have a quick question here. Does propan-3-amine exist? And the answer, similarly to our alcohols earlier, is no, because while there are 3 carbons, it's going to be on the, we're going to try and minimize that number. So we're going to try and minimize that number. If we number this one 1, 2, and 3, if we put it on this end carbon, then that would make that carbon number 1 instead. So we're going to use minimize the carbon numbers. Now, if there were multiple functional groups attached, then you'd have to consider the priority of those groups and which one's more important, in which case that substance or that functional group would have its number minimized. But because we don't do that in this course, you don't have to worry about it. Now, I've covered the first 3, including the options for propanamine. Now I want to give this a go where we name another one that is substituted. So we have a carbon chain that's not just a straight chain. We are going to name or number these carbons from the side that gives us the lowest number for the position of the amine. And as you can see, actually I'll just do it here. As you can see, we have on carbon 3, I'm going to try and do it a little bit more advanced now. Instead of just starting from the right-hand side, as in the end of the molecule, I'm going to start from the beginning. We know that our carbon number 3 has a methyl group, so we'll name 3-methyl. And then it has 4 carbons, so meth, eth, pro, but. So then we know it's 3-methyl butane 2-amine. So the butane 2-amine tells us that our nitrogen, our amino group, is coming off of carbon 2. The longest chain is 4 carbons long, and then on carbon 3, which is adjacent to the one that our amino group is on, is where we have a methyl group. So it's similar to the substituted alcohols. Instead of having ol at the end, you have amine at the end, but otherwise it is the same. Now let's double check. We don't have to, by the looks of it, name any diamines, but just for your sake, just to show that you have the ability to name some of them at least. If we have this structure here where we have 1, 2, 3, 4, 5 carbons in our chain, and then we have amino groups on each end, the molecule will be called pentane. First of all, we keep that E because the ending has starts with a D now. So pentane 1,5-diamine tells us that it's 5 carbons in the main chain, and then on carbons 1 and 5 we have amine groups. So again, you don't have to worry about naming those because they're not in the course, but you can see that the naming schemes are similar to before, and you could do it. Now, the last bit of information that you need to know, or at least you probably should have known already, but amines can act as bases. Now, you will have seen, and I'll rub this out in a second because I don't want it here for too long, but you will have worked with ammonia, or you should have known ammonia is a base. And similarly, amines, which are obviously our carbon-containing structures, are also going to be bases. The reason is because the nitrogen atoms themselves have a lone pair of electrons that can interact with protons from an acid. Now, this amine here, so we might as well try and name it while we are here. We have carbon 1, 2, 3, 4, and I'm naming that again to put the number 1 carbon as close to the nitrogen as possible. So this is going to be similar to before. It'll be our meth, eth, pro, but. So it'll be butane 1-amine with our 3-methyl group attached. So it's actually quite similar to the previous one, except for the amine group is now on carbon 1 instead of carbon 2. Now, the important point here is that if this molecule is put into a basic environment where there's a lack of H+, our molecule is going to look just like this, just like a regular amine, 2 hydrogens on the carbon, and then, 2 hydrogens on the nitrogen, and then the nitrogen will be attached to the rest of the carbon chain. However, if you put this into an acidic environment where you add some extra protons, what will happen is, as I mentioned before, you have the lone pair of electrons on the nitrogen, and that will make this act as a base. So the proton, the H+, will come along. It will join to our nitrogen's lone pair, making a bond. It will leave the nitrogen positively charged, but that is more stable. That's more stable than having this molecule plus a lone H+. So in an acidic environment, we add on an extra proton, and we have to put a positive charge on that nitrogen as well to take into account the fact that it has essentially lost a share of an electron. Now you notice the nitrogen here has 1, 2, 3, and 4 bonds. So because it has 4 bonds, which is greater than the 3 that it's expected to have, that's when it's going to have a charge on it. Cool. Now, I've got a point here, and I just realized that I haven't fully answered one of the other points that is up here, but I'll do that in a second. So I've written there that specifically each amine will have a pH at which they'll be roughly 50-50 ionized and unionized, and that is called their pKa. So that will be a number. So they'll give some, for a particular amine, it'll have a pKa value, and that tells you that you'll have half and half in both these states, this one here and this one here. If you are at a pH above, so in a more basic environment, then you're going to have a majority of this. Other way around. If you're in a basic environment, you're going to have a majority of this form here. Whereas if you're at a pH that's lower, so more acidic, then you're going to have the protonated form as being the majority. Now here we have this last point here, which was explain why the protonated form of an amine is more soluble in water. And the reason is that this one here, so this first one, we have obviously dispersion forces because they're always there. You get dipole, but you also get hydrogen bonding with water, which is it's a good interaction. It's a stabilizing interaction. Now we have this one here that will have the same ones as before, but it'll also have ion dipole bonding as well. Now, on the scale of intermolecular force strength, hydrogen bonding is one of the strong ones, but ion dipole is even stronger. So ionic bonding is sort of classed as an in-between, or no, it can be classed as both an intermolecular and an intramolecular force. But in this case here, ion dipole is a stronger intermolecular force than hydrogen bonding. And whenever you have a stronger interaction, that is going to be more favorable. In which case, this protonated version of the amine is going to interact with water more favorably than the non-protonated version, which will make it dissolve more easily. It can get in between the water molecules because the water molecules are happy to have that interaction with it. Cool. And I think that's pretty much it for this. So I hope this has helped.